Okay, welcome back to the trigonometry YouTube series. So I didn't post in a little while, so a bit longer than a week because I was a little bogged down with schoolwork. Okay, so you may recall that last time we introduced these trigonometry functions. We talked about what trigonometry is, and we kind of just said mainly that cos, sine, and tan are the three most important ones, the most common ones, while the other ones, so secant, cosecant, and cotan, um, those are very rarely used and kind of just almost never. All right, but we may be asking, well, what's the point? Like we introduce all these things, but there's no point to it, and we haven't seen any applications. So let's take a look today at some applications, in addition to some common values that will appear in cos, sine, and tan. And of course, that translates to the other three. All right, so let's take a look at what we can do. So the first thing, the one that's easiest to work with, is going to be a right triangle. So let's say we have a right triangle that looks like this. So it has a hypotenuse, let's say r, and the right angle is over there. And let's say here's an angle theta. Well, trigonometry, as I mentioned last time, it originated as the study of triangles. So we should be able to figure out the rest of the triangle using trigonometry. Now, this last angle over here, we don't really need trigonometry. That's just angle chasing. So because the angles of a triangle add up to 180 degrees, and we already have a 90-degree angle, this angle is just going to be 90 minus theta. Okay, but then what about these other two side lengths? Don't really know what they are. So trigonometry gives us the power to solve that. So let's draw in an axis system. So x, y axis, and over here, let's just draw in a circle. Okay, so notice that this looks kind of the exact same as the unit circle, right? Like if you don't look at the height and the angles, if you just look at this angle theta and how the terminal arm is kind of rotating up like that, then it kind of looks like, well, the coordinates of this point, as we mentioned last time, will just be cos theta comma sine theta. And that's almost the case. We just need to factor in this additional r. So remember that before when we had um, our trig functions and we defined it, it was all on a unit circle. So a circle of radius 1. Okay, but now we want a circle of radius r. How are we going to modify it like that? Well, we're just going to dilate everything or expand everything by a factor of r. So it's kind of like zooming in or zooming out depending on what r is. So if we, let's say, zoom in by a factor of r, then all of our coordinates are going to be multiplied by r. And we're zooming in relation to the origin. So origin is the one point that doesn't change. But everything else will be multiplied by r. There we go. So we're just going to adjust the coordinates. And that's going to be r cos theta and r sine theta. What does that tell us? Well, when we look back at our triangle, we now have a triangle that has a horizontal component, right? This is the base of the triangle. And it also has a vertical component, which is the height of the triangle. And of course, the x-coordinate means the horizontal distance. So this horizontal part is going to be r cos theta. And the vertical part is going to be r sine theta. Okay, that's great. So it works on right triangles, which is amazing because right triangles are pretty useful and we're going to see them a lot. Okay, now let's talk about some common values. And we will talk about non-right triangles. That's where we can use things like the sine law and the cosine law, but I'll leave that for later. Maybe next time I'll start talking about one of those. Okay, so now talk about some kind of some important angles that you should know the sine and cos value of that. All right, so let's take a look at this here. So here are the three kind of most important values, and then we can try to figure out everything else from there. So our most important values are 0 degrees, and that one's pretty simple. That's just when we haven't rotated at all, so we can just look at and see, hey, that's just going to be 1 comma 0. So cos of 0 is 1, and sine of 0 is 0. Pretty simple. All right, so the next one is 30 degrees. Maybe it looks something like that. It's floating in space somewhere there. And the last one will be 45 degrees. So this one is kind of like in the middle, and it's somewhere there. Okay. Now that I think about it, I actually lied. I'm not going to do sine law or cosine law next time. We still have a lot to cover before that. Okay. So 0 degrees, really simple. We don't need to worry about that. I'm actually just going to do the 45-degree angle one first, because that one is a lot more, it's a lot easier compared to the 30 degrees. Okay. So let's take a look at this 45 degrees angle. So let's say here's a unit circle, and I draw in at the 45 degrees angle. Something I can notice right away is that this other angle over here is also going to be 45 degrees. They're going to be reflections of each other, and because of that, what we know about this point is that it should be 2 points of the same coordinate. So if it was x comma y, then because it's right on this middle line, and this middle line is actually the line x is equal to y that has an angle of 45 degrees, because of that, we can actually just say that this is going to be x comma x, because they should be the same coordinate. Now, how can I try to find the value of x? Well, I know that it's on the circle, and the equation of the circle is x squared plus y squared is equal to 1. And if you're wondering where that comes from, just comes from the distance formula. So the distance formula states that x minus 0 squared plus y minus 0 squared is equal to r squared. Or rather, it would be like this. It would have a square root and would not be squared. So this is just between x, y, and 0, 0. And we know that the distance between x, y, and the center of our circle should be the radius. So that's kind of where this comes from. And in this case, the radius would be 1. So you square both sides, and this inside the square is just x squared plus y squared. So it's really not hard to see how you can go from the distance formula to the equation of a circle. All right. And the important thing here is that since both the x and y coordinates are the same, I can say that x squared plus x squared is equal to 1. So then I can say that x squared will be 1/2. So then I can say that x is equal to 1 over root 2. Or you can rationalize, you can write it kind of in the more standard form, root 2 over 2. But both of these values mean the exact same number. Okay, so what does that tell us? Remember, this is equal to cos theta sine theta, which is in this case 45. So that tells us that cos of 45 degrees is equal to 1 over root 2, or you can write it as square root 2 over 2. And it also tells us that sine of 45 degrees is equal to 1 over root 2, or square root of 2 over 2. Okay. And then the last part is the 30 degrees angle. So actually for the 30 degrees angle, we're not going to look at the unit circle just for now. And we're going to actually be using the this kind of relationship that we had before, where we said that it's going to be if the side length of a right triangle, the hypotenuse, is r, then the other two sides are going to be r cos theta and r sine theta. And r cos theta is kind of the leg that is adjacent with the angle. And the one opposite the angle is going to be sine theta. All right, so let's take a look. So let's first of all just draw an equilateral triangle. A nice little friendly equilateral triangle. And let's draw a height of this equilateral triangle. So because it's an equilateral triangle, I know all of the angles will be 60 degrees, and therefore this angle over here will be 30 degrees. Now, it doesn't really matter what the side length is. So let's say the side length is 2. This will make it easier on us. And because it's equilateral, it has so many good properties. First of all, this height is also an angle bisector, and also this height will be a median. So it will bisect the side length over here. And that just means to cut it in half. And if you think about an equilateral triangle, that should be the case because it has so many symmetries. So since this side length would also be 2, and it's cut in half, each of these smaller side lengths are 1. And what that tells us is, remember that another way to write this side length over here, instead of writing 1, I could write it as 2, sorry, this one's opposite, so it would be 2 sine of 30 degrees. And I know this should be 1. So I can solve and I can say sine of 30 degrees is equal to 1 half. Okay. And now to find the equivalent cos of 30 degrees, I would be able to write 2 times cos of 30 degrees is equal to the height. Okay, let's find the height. Well, I know from Pythagorean theorem that this is just going to be the square root of 2 squared minus 1 squared. And that's the square root of 4 minus 1 equals to the square root of 3. So then I can say that cos 30 degrees will be the square root of 3 divided by 2. Okay. Now, why? So why are these three really important? Right, so I had the 0 degrees, 30 degrees, and 45 degrees. Well, actually the thing is, I lied. These three are not the only three important ones. Let's draw on our unit circle again. Really, there's a lot of most important ones. So obviously you can imagine that each multiple of 90 is going to be pretty important. But, those aren't really special. And after knowing 1, so after just knowing the value for 0 degrees, we can rotate our way throughout the entire unit circle, and it's really not that hard to figure out the rest. So 0, 1, -1, 0, and 0, -1. Okay, how about 45 degrees? Well, after I find this 45 degrees, which was 1 over root 2, 1 over root 2, I can actually find 3 other angles. And the 3 other angles I can find, well, I could try to reflect it across the y-axis. So if I reflect it across the y-axis, it's going to look something like this. And this will give me negative 1 over root 2 comma 1 over root 2. Sorry, I don't know how that happened. Okay, and after we see this, we can ask ourselves, well, what's the angle of rotation? Well, I rotated 180 degrees, landing me to negative 1 comma 0. That's a little bit too far. Let's go back 45 degrees. So I rotated 180 degrees minus 45 degrees, 135 degrees. So I can say that cos of 135 degrees is equal to negative 1 over root 2, and sine of 135 degrees is equal to 1 over root 2. Another thing we can do is we can take these 2 points and reflect it across the x-axis. So if we reflect it across the x-axis, we'll get these 2 points. Like so. Now we can ask ourselves, well, what are the coordinates? What is the angle of rotation for this point? And let's say the blue point. Let's label the points actually. So this is green, blue. So we can say the angle of rotation for the blue one, well, we're going to rotate 180 degrees. Then I expect this angle to also be 45 degrees, so 225 degrees. I could also look at it the other way, and I could say that it's an angle of rotation of negative 135 degrees, because I'm rotating 135 degrees clockwise, and clockwise is the opposite of counterclockwise. So I can write cos of 225 degrees equal to cos of negative 135 degrees is equal to negative 1 over root 2. And then we have sine of 225 degrees, the same thing. Okay, and now looking at the final angle, let's say it's, I'm just going to highlight it. It's going to be like this. This highlighted angle, well, that's the easiest way to write it will just be negative 45 degrees, right? But I could also write it as cos of 315 degrees, which is one full rotation, 360, take away the 45 degrees of rotation. So this is going to be 1 over root 2, and sine is going to be negative 1 over root 2. And there we go. So using this one point, we could find 3 other points. And you can see that it's not that hard to figure out the 3 other points, right? You just have to look, okay, where do I reflect it? Where do I reflect it again, maybe, if I have to? And it's really not that bad. Now, for the 30 degrees, a very, very similar process happens. But instead of having 3 new angles, we're actually going to be able to figure out more. So if I draw in the 30 degrees, right, I figured out that cos of 30 degrees was going to be root 3 over 2, and the sine of 30 degrees was going to be 1/2. So you can imagine that I can do very similar things, where I just reflect it across the x-axis, across the y-axis, and so on, so it will look like this. But I also have an additional tool this time. I can reflect across the line y equals x, or this diagonal between the 2 axes. And if I reflect it, then my angle of 30 degrees, instead of being off the x-axis, is off the y-axis, and therefore the total rotation for this is 60 degrees. So this point up here would be cos 60 sine 60. And then since I reflected across the line x is equal to y, I'm just going to take these coordinates, but I'm going to swap them. So that leaves me with cos of 60 degrees is equal to 1/2 and sine of 60 degrees is going to be equal to root 3 over 2. And then from there, I can do the same thing, reflecting and reflecting. Okay. And the very final thing I want to leave you guys with is I want you to kind of ask yourselves these few things for next time. So how can I try to write or simplify cos of negative theta in terms of cos theta or sine theta? How can I write sine of negative theta? How can I try to write cos of 180 minus theta? And then also sine of 180 minus theta. Also, how can I try to write cos of 90 minus theta and sine of 90 minus theta? All right, so I'll leave you guys with those little thinking points for next time. If you want a hint, you can listen to the next part. If you don't want a hint, this is the end of the video. And just like have a great rest of your day and wait for the video next week, I guess. Or if you're already 1 week after where I am, you're going to be able to see the video immediately. But if you do want a hint, look at the same thing that we did before. Ask yourself, now here's the unit circle, and here's the angle theta. What does it mean to have an angle of negative theta? What does it mean to have an angle of 180 degrees minus theta? Where is that on the circle? And what does it mean to have an angle of 90 minus theta? And after you see where that is, ask yourself, now what kind of reflection do I have to use to go from my normal point, cos theta, sine theta, to the point that I want to get to? These 3 points. Okay, so I hope that's helpful, and I'll be answering these 3 kind of mini questions next time.